Okay, let's do our quiz, not quiz, about buoyancy. So, have you ever been on a boat? Um, Hopefully, you've seen some life vests that they have for people, and they're usually these great big bulky things. They're bright orange so that people can see you from far away, and they have a big thing here behind your head, and they usually have a big hunk of foam strapped to your chest, and then there's some kind of straps that go behind your back and around your waist in order to hold it in place. And sometimes they even come down between your legs. Um, this has a lot of disadvantages. One, it's uncomfortable. This area thing near your head is uncomfortable. Two, it's ugly. It's not good. Let's be clear. Um, and so we've designed a new uh, a new life vest. This one is not bulky anymore, so you don't have all this bulk in front of you, which makes it hard to, for example, give your long lost aunt a hug, or you know, do lots of stuff. It also can act as a cushion when you sit, because what we've done is we've taken all of that foam that's here and stretched it out and layered it along the back of your body. So what we're going to do is we're going to have a strap around your ankles here, holding them around the back of your legs, a strap around your waist, some straps around your arms, holding it in place. We have a little thing behind your head so that if you want to lean back and take a little nap, you can. This is amazing. It's going to sell lots and lots of units because it's new and it's awesome. But anyone who's taken fluid mechanics is going to be like, what is the center of buoyancy and mass for each design? Because I'm curious about what the equilibrium position of each person is going to be. So I want you to answer this. Where is the center of buoyancy and mass for each design? And draw it. Okay. Now pause the video here and do it. Don't wait for me to do it. I'm going to take my time. All right. So center of mass for the old light vest. Center of mass is the center of mass of the person. We're going to assume it's roughly right here, coming down. Is that very readable? Not really. Let's pick hot pink. That's not very readable either. Let's try this one. That's better. That's bright. Okay, so here's our center of mass, and that's mass times gravity. And then the center of buoyancy, though, is going to be acting one on this vest, right? And one on this vest. We add those together, and we find out that the center of buoyancy is somewhere over here, acting up. So this is FB for this object. Great. So that's the center of buoyancy and mass for that design. Now for our new hotness, our center of mass is the same, right here, acting in the gut, going down, M times G. But our center of buoyancy is going to be over here, going up like this. That's our FB. Great. Cool. Oh, I forgot. There's extra cushion on your feet too, so don't forget about that. You're going to want one of these. So we've drawn that. Now we want to know what direction will each person rotate and when will they stop. So let's draw that first. So in this case, let's draw the direction that they will rotate. Our FB is going up this way, our MG is going this way, so our combined forces are going to produce a couple in this direction. That's our rotation force. And then for our new hotness, it's going to produce a couple in that direction because we have our FB coming up in this way and our MG going down this way, and it's going to produce a couple that rotates in that direction. So now, when will they stop? Draw each person in their equilibrium position and make sure you draw in the buoyant and weight forces. All right. So we know that if they're in an equilibrium position, what's going to be true about their buoyant and weight forces? They're going to be collinear, right? They're going to be collinear. So now let's draw both of these people. So I'm going to draw some water, and I'm going to draw this guy, he's got a, here's his life vest. And then here's our stick figure guy. His head's above water, thank goodness. Here's this. Well, let's actually undo that. Here's his arms. And his legs are coming out like this. And he's happy. Although, who knows if that actually looks happy. So, anyway, if we draw our buoyant and our weight forces, I'm not going to use red this time because I've already used red for that. Our buoyant force is going to be acting somewhere in between over here. And our weight force is going to be collinear with it, acting down. Mg and F buoyant. Great. Now, if we draw our great new just wait there's more design, what we're going to see is that our life vest is going to float like this where it wants to. Like that. And our person is going to be here. Well, he's not Mr. Ovalhead. So let's undo that. Our person is like this. Both arms just hanging down. And they are not happy because they are underwater. But all their forces are in equilibrium. So our FB is going to look like this, and our MG is going to look like that. So, would you buy this new life vest? No, you would not. Turns out there's a reason life vests look the way they do. Okay, so now here's a question that's really interesting. Let's try to solve this. How much foam would it take to float an average human? Okay, so we know that the mass of the human is 75 kilograms. The specific gravity of a human is 1.03 kilograms. So you're slightly heavier than water per volume. And the mass of the density of the foam is 30 kilograms per meter squared. So what we're asking is how much foam would it take to float a human? So let's draw well, first of all, let's draw some water. We have a mass of foam underwater, and on top of it, a person. Just doing awesome. He's singing. And he's happy. So, we have a person sitting on foam. The foam is just submerged because it's how much foam will it take to float an average human, not how much to float them comfortably. And we want to then figure out how much this would be. So, we're asking for an equilibrium, right? We're asking how much foam would it take to float an average human. We're dealing with forces. This is less obvious than normal, but we're still going to need a model where we use sum of the forces equal to 0. So our model is going to be sum of our forces is equal to mass times acceleration. But we're going to assume, fluid at rest, and density is equal to a constant. And we're also going to use as a model our buoyant force, FB, is equal to rho g times our volume. Great. So that's actually equation 2. So equation 1 into equation 2, we know that because of A, and we haven't been doing this, but I'm going to try to start doing this more. A and B, we know that this is equal to 0 from A. Again, we're trying to tell our graders exactly what assumptions we're using where and how. And we get that the sum of our forces in the y direction is equal to 0 is equal to, and if we're doing a free body diagram of our foam, what we will do is we'll say that there's a buoyant force here, there is a weight here, and there is a force due to the, sorry, not M human, F human. force due to the human on the foam. So let's add all those together. We have negative mass times gravity, but our mass is really just our density of our foam times volume times gravity. We know that our buoyant force is equal to rho plus density of water times gravity times the volume of the foam, right? Because the foam is just barely submerged. And then finally we have to subtract the force of the human, which is just m human times g. Great. So now we solve this. Let's check and see how many unknowns we have. We know this, 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 we know this. We don't know the volume of the foam though. So it turns out we can say that m human times gravity is equal to, actually we can cancel out all the gravities now that I think about it. So the mass of the human is equal to the volume of the foam times rho of the water minus rho of the foam. And just occurred to me that I've been using foam, that's right. Yep, it's not PHOAM, it's FOAM. Great. Cool. All right, so this is easy to solve. We have 75 kilograms times divided by 1,000 kilograms per meter cubed minus 30 kilograms per meter cubed is equal to our volume. And once you know it, I haven't solved it and I don't have a calculator. Well, let's do it real quick here. Hopefully you're doing it with me and you're doing it faster than I am. We take 75 and divide it by 970 divided by 970, and that is equal to 0.07 cubic meters. Volume is equal to 0.07 meters cubed of foam. Great. Now, here's a bonus question, and I'll let you chew on this, and we'll just chat about it. Is this stable? Is this stable? Pause the video and draw what happens if we perturb this system a little bit. Now, perturb usually means a small change in a variable. So in this case, we're worried about what happens if this person sitting on top of this thing accidentally leans a little bit and our entire object rotates a little bit in this direction, let's say. At which point, we can draw his center of mass. We know the center of buoyancy is acting still at the center of this. So what happens if he leans over just a little bit? Is this stable? Pause the video, or don't pause it, and write down an answer. And the answer is no. No. Which anyone who's tried to stand on a foam block could easily tell you. It's incredibly unstable. The second he leans over a little bit, his weight is acting in this direction, but the buoyant force is still acting up, and that couple acts to continue to rotate the person in the direction they rotated to cause the instability in the first place. So it is an unstable equilibrium, and you have to continually work to keep stable in it. Right? This is why boats are usually hollow, and you put your weight in the middle at the bottom, so hopefully your weight acts on the bottom. And also, boats usually act so that if you tilt them a little bit, the center of mass shifts in the direction that you tilt them. Center of mass of the submerged water, so the center of volume of the submerged volume, the centroid of the submerged volume, shifts in the direction that you rotate, so that the buoyant force rotates faster, hopefully, than the mass rotates, and so you maintain a couple that orients you upright. Great.